Welcome back to the deep dive. Today, we are moving beyond the more abstract discussions of artificial intelligence, and, well, we're strapping in for a pretty rigorous architecture review.
Yeah.
This deep dive is going to fundamentally shift how you think about governance, risk, and maybe most importantly, how you manage your future coworkers, the autonomous agents.
That's the critical pivot, isn't it?
Yeah.
For the last decade, we've really focused on simple automation, where a machine follows a rigid, a deterministic if this, then that kind of script. Now the whole world is moving to probabilistic, goal-oriented autonomy. And this means the agents we deploy aren't just performing tasks. They're synthesizing complex multi-step plans and making real-time, high-stakes decisions based on probabilities.
Not certainties.
Not certainties, exactly.
And what does that profound shift mean for, the human being on the payroll? It means your role is no longer about just rote execution. It's changing dramatically. It's shifting entirely toward high-level governance, nuanced judgment, and precise policy definition. You basically become the editor and the safety net, not the executor.
Absolutely. Our core challenge today isn't primarily about improving the underlying AI model. I mean, that's still happening, of course.
Right.
But the new bottleneck is entirely architectural. It's the interfaces that govern how humans and agents actually interact at scale. We're no longer just automating isolated tasks. We're formally engineering collaboration.
As a system, a measurable governed system.
Yes.
Our sources for this deep dive are really comprehensive. We're looking at a framework for designing robust, safe human agent systems, and it covers everything from the necessary interaction modes and the architecture of engineered escalation, all the way to the complex science of dynamic trust calibration.
You should think of this as the essential blueprint for scaling AI safely inside a large enterprise. The question is, how do you give the machine the speed it needs, which is, let's be honest, the whole point of the investment, without creating systemic, maybe even irreversible risk? That blueprint requires formalized systems for delegation, control, and above all, accountability.
Okay, so let's unpack this then. How do we get the speed of the machine without sacrificing the safety and the wisdom of the human? We have to start by understanding why the traditional sort of simple approaches to managing machine work. Well, why they fail so catastrophically. The shift we mentioned from deterministic scripting to probabilistic autonomy, it's not a small step. It's a deep chasm.
It really is.
These new agents, they synthesize incredibly complex plans, often involving, multiple external tools and APIs. But the very nature of that reasoning means it's inherently unreliable in ways deterministic code just isn't.
It's opaque. It's often very opaque, and it's particularly prone to error when it's operating outside the precise domain it was trained on.
Exactly. And if you try to manage that complexity by defaulting to one of the two sort of historical extremes, either letting the machine run completely free or forcing the human to approve every little thing, the whole system just becomes unworkable.
Right, so let's start with failure mode 1, unconstrained autonomy.
Full autonomy fails because these large-scale reasoning models, despite how proficient they are, they lack two critical elements that you absolutely need for responsible enterprise operation: innate accountability and what the research framework calls dark context.
That concept of dark context is so fascinating and absolutely vital. It's all the organizational nuance, the shifting ethical boundaries, the specific unwritten political risk.
Stuff that's not in the manual.
Exactly. The unspoken operational rules that no mathematical model can ever fully absorb. So, for example, an agent might follow a policy rule perfectly, but it fails to account for the fact that a specific client flagged in the system is a high-level strategic partner whose data should never be touched without executive sign-off, regardless of what the standard policy says.
Right. The agent sees the data and the rule, but it doesn't see the political gravity. And without formal governance structures, you introduce a systemic and catastrophic risk, the hallucination cascade.
And this is not just a theoretical thing. A hallucination cascade happens when an initial fundamental reasoning error, let's say, the agent incorrectly interprets a key regulatory filing, or it misclassifies a piece of inventory.
A small mistake at the start.
A small mistake that then propagates through a subsequent sequence of tool calls.
Can you give us a concrete example of how that propagation works?
Sure. Imagine an agent that's tasked with optimizing cloud infrastructure spending. It hallucinates that a certain legacy database cluster is redundant because it, misread the changelog.
Okay.
It then proceeds to synthesize a plan. Step 1, back up the cluster. Step 2, swing down the resources. Step 3, delete the snapshots.
Oh, no.
Because that first faulty assumption redundancy validated the entire plan. Every single subsequent tool call that's based on that flaw just amplifies the damage.
And because the agent is unconstrained.
This cascade can lead to irreversible data loss or a major production outage before a human even sees the first alert. The system optimized brilliantly for the wrong goal.
Wow. That sounds like a system optimizing for total failure because it was just way too confident in its starting assumption.
Precisely.
But as a countermeasure, you often see organizations swing immediately to the other, equally destructive extreme, exhaustive, human-in-the-loop validation.
Which is failure mode 2. And that collapses productivity instantly. If you require mandatory blocking approval gates for every discrete low-level action, approve deleting temporary file 1, approve running database query 42.
The human operator immediately becomes a manual bottleneck.
For processes that should be running at machine speed, this induces not just latency, but extreme latency across thousands of parallel workflows.
Which very quickly leads to the phenomenon we all know as alert fatigue. The system just floods the reviewer with hundreds, maybe even thousands of requests every day, and many of them are really low stakes.
And the human's natural response isn't to think harder about each one.
No, it's to clear the queue faster to get back to their real job.
Precisely. The reviewer, totally overwhelmed by sheer volume, begins to rubber stamp the low-stakes requests. And critically, this habit of automated approval carries over. They stop exercising critical judgment even when a high-stakes request appears. This failure isn't a technical flaw in the AI, it's an organizational flaw. It comes from a lack of engineered delegation that fails to distinguish systematically architecturally between what is a routine action and what is a high-stakes exception. #FAB. Defining collaboration quality.
So, if full autonomy is way too risky and exhaustive human oversight is just way too slow, where is the sweet spot? The sources define this ideal middle ground as collaboration quality. And importantly, they stress this is a measurable system property, not just some fuzzy feeling of teamwork.
Absolutely. The goal is a highly functional hybrid team that balances machine speed with human oversight safety. Collaboration quality is characterized by what's called the intertwinement score.
The intertwinement score.
Yeah, it's a fascinating metric that quantifies the degree to which humans and agents contribute their unique complementary strengths without actively interfering with or duplicating the other's primary function.
That idea of mutual non-interference is really powerful. It means the human isn't sitting there fact-checking the agent's basic calculations.
Right.
And the agent isn't just sitting idle waiting for permission to execute some routine API call. The human handles the why and the policy, and the agent handles the how fast and the sheer volume.
And the primary friction point that actively degrades this intertwinement score is misaligned trust. If the trust relationship between the human and the system isn't objective and precisely calibrated, the system fails, regardless of the underlying model's accuracy.
And we're talking about two specific kinds of trust failure here, right? And they're both equally damaging to the bottom line.
Yes. First, we have overtrust. This leads directly to automation bias, where human vigilance just drops, simply because the suggestion came from a sophisticated machine.
Okay, so like a system proposes a deeply flawed or risky financial plan. The human reviewing it just approves it without checking the underlying evidence or the source data. Thinking.
The AI model is too complex and expensive to be wrong. This is exactly how high-stakes rubber stamping happens.
The human is essentially outsourcing their critical judgment to the machine, not because the machine earned it, but because the human got complacent.
Yeah.
And the reverse of that is undertrust.
Undertrust leads to system disuse. So if the agent is actually highly reliable, let's say it has a verifiable 99% success rate on its designated task, but the human doesn't trust the interface or the output or the organization's overall commitment to agent safety.
They'll just do it themselves?
They will manually duplicate the agent's work. They'll run the parallel manual process just to verify the machine's output, or they'll just revert to the old manual processes entirely.
And when that system disuse happens, the entire return on investment of the agentic workflow is just neutralized. The technology works, but the human management layer makes the deployment fiscally ineffective. The key takeaway from the sources is that we have to engineer the trust layer itself, making it objective and dynamic, which is a major focus of this deep dive.
It is.
But first, we need to understand the formal spectrum of interaction, because the control configurations are far more granular than just being in the loop. When the sources talk about interaction modes, they really emphasize that these are not just different user interface patterns, like, where a button is placed.
Not at all.
They are formal control configurations that architecturally define two things. First, which actor holds the initiative, who starts the action, and second, which actor holds the veto power, who can stop or modify the action.
This taxonomy is absolutely critical. It dictates the maximum level of autonomy the system is allowed to operate with, which directly correlates to the enterprise's risk exposure on one side and its productivity gain on the other.
Right.
You have to select the mode that's appropriate for the task's inherent risk.
So let's start with the one everyone is familiar with, Mode 1, Human in the Loop, HITL. This is the lowest level of autonomy, right? Typically 10 to 30%, and it's explicitly human-led.
The mechanism here is that mandatory hard-blocking approval gate for every single discrete step of execution. It's the right mode for early deployments or tasks involving unverified agents, or for extremely high-risk, irreversible actions like deleting critical production resources.
But the moment you choose HITL, you accept the primary failure mode, the human latency bottleneck.
Oh, yeah.
If the agent needs to perform 50 steps to complete a task and the human has to approve all 50, that task takes hours, not seconds.
To mitigate this, the underlying architecture has to be, well, brutally unforgiving about human responsiveness. You have to enforce strict session timeouts that fail closed if no human response is received within the agreed SLA.
The system can't wait.
It cannot wait indefinitely. If the human reviewer is delayed by 5 minutes, the entire process must either abort gracefully or roll back to a safe state. Waiting just introduces cascading errors and data staleness.
Okay, so moving up the maturity curve, we find Mode 2, Human on the Loop, HOTL. This grants a much higher level of autonomy, typically 60 to 80%, and is definitively agent-led.
In HOTL, the human transitions from being the mandatory approver to being more like a safety driver or a supervisor.
Okay.
The mechanism is real-time supervisory monitoring with non-blocking asynchronous override capability. The agent proceeds with its plan by default unless the human specifically steps in to halt it or divert its course.
So the human is mostly just watching a dashboard. What's the primary risk that gets introduced here?
The primary failure mode for HOTL is insufficient transparency, which leads to a loss of situational awareness.
Right.
If the system doesn't provide the human with enough synthesized, high-quality detail through real-time dashboards, state visualizations, audit trails, the human loses context about why the agent is doing what it's doing.
And when they finally try to intervene?
They're intervening blindly, making the override ineffective or even counterproductive. This forces the system architect to invest heavily in that visualization layer, #B, advanced invariance modes.
Okay, now we get to the configurations that, to me, seem to truly solve the alert fatigue problem. The favored model for mature production systems is Mode 3, Human on Exception. This involves high autonomy, often 80 to 90%, and it's definitively context-dependent.
This is the model that preserves human cognitive energy. The agent executes all routine, low-risk, and well-understood tasks completely autonomously. It only initiates a blocking escalation when predefined risk thresholds are breached or when the action is unprecedented.
So the magic here is this concept of predictive escalation. The system isn't waiting for the agent to fail.
Right.
It's using that independent risk scoring service, which we'll get into, to identify potential failures or novelty or uncertain scenarios before the action executes. It filters out the 90% of noise and surfaces only those truly novel or critical cases to the human.
It completely reverses the burden of proof. The system assumes successful, safe execution unless the objective risk score flags it as a mandatory exception. This optimizes for throughput while maintaining safety.
Okay, contrast that with the highly specialized Mode 4, Human as a Service. This is the flipped hierarchy, still agent-led, but with variable autonomy.
Yes, human as a service formalizes the agent's dependency on ambient human knowledge. In this model, the agent is the master, and the human is invoked as an external tool to resolve specific gaps in the agent's context or capabilities.
Wait, so the human is the tool in this case?
The human is the tool. Imagine an agent tasked with onboarding a new vendor. It gets stuck because it needs a specific security key, or it needs someone to physically confirm a delivery address, or maybe it lacks the required credentials to access a legacy system.
So instead of failing,
the agent initiates a human as a service call. It provides a detailed input payload and expects a specific output, a credential, a confirmed address, an approval signature that it can then consume and continue its process.
So it's a formalized way for the agent to say, I don't know this, or I can't do this, rather than just hitting a wall and hallucinating the necessary information. That forces the human intervention to be highly structured and efficient.
Exactly. And finally, we have the two strategic modes that define the system boundaries and the overall learning structure.
Mode 5, policy author. This operates at the highest strategic level.
Yep. The human defines high-level business constraints, ethical boundaries, the goal hierarchies. And crucially, they define the norm kernel, the immutable set of ethical and operational rules the agent fleet cannot violate, regardless of its immediate goal optimization.
The failure mode here would be goal misalignment, right?
That's it. The agent might successfully optimize for a narrow metric, say, maximizing conversion rates in an automated marketing campaign, but at the expense of systemic stability or long-term customer trust, thereby violating the broader high-level spirit of the norm kernel set by the policy author.
And finally, mode 6, corrective signal. This is entirely after the fact.
It is. The human reviews completed execution traces, the full audit of steps, inputs, and outputs, and provides reinforcement signals. This is the crucial mechanism for continuous learning, allowing expert corrections to tune the agent's internal reasoning policy, weighting, and prompt structure for future iterations. It closes the loop.
Between execution and refinement.
Exactly.
Okay, we've established the spectrum of interaction. Now, how do we build the actual machinery that makes these dynamic shifts in autonomy possible? The sources insist that to manage these diverse modes at scale, you need a robust modular architecture.
And the foundational principle is a strict separation of concerns. You absolutely must separate the reasoning core, the agent itself, from the governance layer.
The system that ensures safety, compliance, and human alignment.
Right, and this governance layer is complex. It's not just a simple API gateway. It's a collection of specialized services designed to intercept, assess, and manage risk in real time before the agent can commit a harmful action.
So what's at the heart of that?
The central nervous system of this entire coordination structure is the escalation engine. It operates continuously, consuming a stream of agent telemetry, the planned actions, the specific tool parameters the agent wants to call, and the agent's own internal confidence intervals.
And it evaluates all that against a formalized trigger registry.
That's right.
The trigger registry being the master rulebook. So what is the engine's fundamental purpose?
Its primary function is to enforce boundaries. It prevents the agent from exceeding its predefined delegation charter. It's the constant real-time enforcement arm of the system, making sure that an agent authorized for Tier 1 tasks never accidentally executes a Tier 3 action.
Okay, that sounds great in theory, but how does the system enforce this physically, right at the point of execution? What is the architectural choke point?
The enforcement mechanism is architected as a blocking interceptor that's positioned at the core tool call layer. Think of it as a mandatory security guard that's positioned directly in front of every sensitive API, database, or resource endpoint. Before the agent can actually execute a high-stakes command writing to a production database, spending corporate funds, sending an external communication, it first has to present a signed approval token.
So the agent has to ask the escalation engine for that token first.
Precisely. The engine reviews the request against the trigger registry, and if the risk is deemed too high, or if the action falls outside the agent's current trust score threshold, the engine blocks the tool call entirely until a named human decision-maker generates and signs that token. This interceptor is mandatory. It's non-bypassable.
Ensuring all high-risk actions pass through the governance layer first.
Every single time. ##B. How risk is measured independently.
Now, here is where we address that confidently incorrect problem we talked about earlier. The system cannot rely solely on the agent's self-assessment of its own reliability. That's just a massive blind spot.
Absolutely not. To provide objective safety, you need an independent audit function, one that is isolated from the agent's own reasoning processes. And that's the job of the Risk and Confidence Scoring Service.
Right.
This service uses separate, often much simpler models or deterministic verifiable rules, not the agent's complex, opaque internal thinking, to provide an objective metric for autonomy.
So this is a dedicated, separate microservice, and its only job is risk assessment.
That's it. It calculates two primary mandatory scores for every proposed action. The first is the impact score.
And what goes into that? Why can't the agent itself just calculate the impact?
Well, the agent can estimate the impact, but the impact score service provides the enterprise's objective, quantified risk calculation, It quantifies the potential cost of the action, financial, regulatory, security, reputational damage based on the specific resource being targeted.
So the agent might think deleting a specific file is low impact.
But the impact score knows that file resides in a highly regulated database. The service prioritizes organizational risk tolerance over the agent's self-interest.
Got it. And the second score?
The second is the uncertainty score. This is derived from analyzing the agent's internal measure of its plan's reliability, often monitoring things like model logits or the consistency of its internal state representation. It asks, how sure is the agent that its output actually aligns with the prompt?
But again, this has to be evaluated by the independent service.
Yes, to prevent the agent from simply claiming high confidence when it's generating complex novel plans.
So the integration of this objective risk score is the linchpin of the whole thing. It is a mandatory input for the escalation engine's decision logic.
It is the absolute gatekeeper. The decision to escalate is based on the system's objective risk metrics, irrespective of the agent's subjective confidence. If the agent says, I am 99.9% confident this plan will save $10,000, but the independent risk service calculates a Tier 3 high impact score because it involves moving sensitive client data.
The system escalates.
The system escalates regardless of the agent's internal belief. ###C. The 5 categories of escalation triggers.
Okay, so the escalation engine consumes that objective risk score and then checks the proposed action against its trigger registry. The sources really stress that escalation must be treated not as some error handler, but as a formal, predictable state transition managed by policy.
Exactly.
So let's look at the 5 categories of formalized triggers used to define this critical transition point.
Category 1 is risk-based escalations. These are triggered entirely by the target resource's inherent sensitivity or the operation's inherent gravity. This is maybe the most crucial type for ensuring basic safety.
And this directly prevents overprivileged agents, which is just a massive security vulnerability.
Yeah.
An agent might have permission to read all data, but it must be blocked from deleting critical data.
Exactly. This requires a formalized resource risk manifest. This manifest maps every specific tool, API call, or database field to an intrinsic risk level. So if an agent attempts to access a resource marked as Class 1, highly sensitive data, or perform a Tier 3, irreversible financial transaction, the system blocks and escalates immediately.
It doesn't care about the agent's logic at that point.
No, it only cares about the potential damage.
Category 2 is uncertainty-based escalations. This directly addresses the probabilistic nature of the agent itself.
Right. If the agent's internal confidence calibration, its measure of epistemic uncertainty, meaning how unsure it is of the underlying facts, if that exceeds a predefined threshold, it signals the agent is operating in highly novel territory or outside its training distribution.
This is the structural defense against that confidently incorrect behavior we keep mentioning.
It is.
How can the system verify this uncertainty independently?
Well, one method is using an independent critic agent. A second, smaller, specialized model may be trained solely on identifying logical inconsistencies or resource boundary violations. The critic agent reviews the plan and provides a separate objective confidence score.
And if the scores are too far apart?
If the difference between the primary agent's confidence and the critic agent's confidence is too high, it triggers the uncertainty-based escalation.
Okay. Moving on, we have the practical operational management triggers. Category 3 is cost-based escalations. This moves beyond data integrity to resource consumption.
This is essential for preventing financial hemorrhaging. Triggers are activated if a single goal execution exceeds a preset token budget or an API spend limit within a specific time window.
The guardrail against catastrophic recursive planning loops.
That's it. We've seen those in poorly constrained agents, where the agent starts generating massive, repetitive queries or plans that consume thousands of dollars in minutes without achieving any tangible outcome.
That's a nightmare scenario. The AI is just stuck, burning cash at an exponential rate. Okay, category 4. Time-based escalations.
This manages stagnation and prevents indefinite waiting. If an agent initiates a task and fails to reach a terminal or save state within a predefined resolution SLA, service level agreement, the system escalates.
Identifying agents that are stuck.
Stuck spinning on a subproblem or caught in an undetected infinite loop. This ensures the human can intervene to terminate the agent, recontextualize the goal, or fix an external dependency.
And finally, category 5. Policy-based escalations. These are the hard, deterministic business rules.
These are static requirements integrated directly into the orchestration logic. There are non-negotiable compliance rules, like any transaction involving a counterparty in Region X requires review by legal, or all lease adjustments over a certain monetary threshold require human review.
Yeah.
These rules are often codified in configuration files, and they provide a bedrock of regulatory compliance that complements all the probabilistic risk triggers.
So by formalizing these 5 diverse trigger types, from resource sensitivity to agent uncertainty to hard business rules, the enterprise can manage thousands of diverse agents through one central, auditable governance plane.
That's the goal.
So we've established when an escalation must happen. But the moment that trigger fires, the system has to pivot entirely. It shifts from optimizing the agent's action to optimizing the human's decision-making interface.
Yes.
And this transition point is managed by the task context packaging service.
This service's entire job is what we call context engineering. It has to synthesize the agent's internal state, which can be a sprawling log of thousands of steps, tool calls, and intermediate thoughts, into one concise, clean, and actionable decision packet for the human reviewer.
The core guiding principle for this service is minimal sufficiency.
It is. The packet must provide the minimal but sufficient evidence needed for the human reviewer to make a fast, informed choice. If the packets are too lean, you get evidence gaps, and the human can't perform their due diligence. But the sources highlight that the greater, more common risk is the overly verbose packet.
I can absolutely imagine that being a huge problem. If you just dump 100 pages of debug logs and internal reasoning traces on a reviewer, they'll just look for the summary line and assume it's correct.
Exactly. When packets are overly verbose, the critical risk details are effectively hidden in a sea of irrelevant logs. It leads to information blindness.
Yeah.
The human gets tired of wading through the noise and falls back into the habit of rubber stamping. The system essentially weaponizes data density against the human's finite attention span.
So the packet structure has to enforce a strict mandatory schema requiring specific fields to ensure it is decision-ready before it even enters the human queue. Let's detail that structure. What are the mandatory elements the human must see to do their job effectively?
First and foremost, a clear, unambiguous decision request. It needs an articulated goal and the required action, phrased simply like, the agent requests permission to execute a $50,000 purchase order for vendor X, deviating from standard budget by 10%. No ambiguity, no hidden context.
Okay. Second, and this seems crucial for the human to validate the agent's critical thinking, the packet must show the proposed action and the rejected alternatives, plus the reasoning for choosing the proposed path.
This is non-negotiable. It shows the human that the agent actually considered multiple viable paths, thereby validating its internal search and prioritization process. If the agent only presents Plan A, the human has no basis for assessing the decision quality.
Right.
Third, the risk and confidence indicators. These have to synthesize the independent audit scores we discussed, presented as clear visual cues, like a red, yellow, green indicator, alongside scores like Impact Tier 3 and Uncertainty Score 0.95.
And finally, the stakes have to be transparently clear.
Correct. The packet needs to state the expected impact and reversibility, explicitly saying if the action is destructive, irreversible, or fully reversible within 24 hours. This automatically demands higher scrutiny from the reviewer and feeds directly into the prioritization engine for the human's queue, ##B, preventing human bottlenecks and fatigue. Even with perfectly structured packets, we have to remember the foundational principle of cognitive ergonomics. Human cognitive bandwidth is finite, and it's easily destroyed by interruptions. If we fail to manage the flow of work, we just reintroduce the productivity collapse we sought to avoid in the first place.
And the primary architectural challenge here is avoiding and mitigating escalation storms.
An escalation storm is the modern equivalent of the IT department's panic room scenario. It happens when a systemic, fleet-wide change, like a sudden dependency failure, a network outage, or a poorly vetted model update that introduces a minor but widespread logical error, causes a near-simultaneous surge in escalation requests across the entire fleet of agents.
And that immediately overwhelms human capacity.
And can lead to a total system halt or massive paralyzing backlogs.
So we need active escalation traffic management to flatten that peak. What are the mitigation strategies the sources emphasize?
Number 1, rate limiting. This means enforcing a maximum number of blocking escalations per individual human reviewer per time window. If the queue for a specific reviewer exceeds a defined operational capacity, the system has to trigger graceful degradation.
Like redirecting flow or shifting the agent fleet to a safe mode.
Yes, a mode where only low-risk, read-only tasks are performed.
Okay. Number 2.
request deduplication. This is about optimizing the human's time. If 50 different parallel agents independently encounter and fail on the exact same API error because of an external service disruption, they should be grouped into a single management decision for the human to resolve once.
Instead of requiring 50 separate identical approvals or corrections.
Right. And number 3, batching and time boxing. For low-priority escalations that are not time-critical, say a request for information that can wait an hour, the system should stack these tasks into scheduled batch review sessions instead of triggering interrupt-driven alerts. This significantly reduces the devastating cognitive switching costs caused by constant, unpredictable interruptions.
And before any of those 3 strategies even come into play, we must have robust automated pre-filtering.
Absolutely. Simple issues like a missing data field, a temporary network glitch, a non-critical error that the agent has a known fix for should be intercepted by a pre-filter service or handled by specialized self-correction agents that attempt to retry the task with better context.
Failure to filter those trivial issues leads directly to alert exhaustion,
Where the human operator stops analyzing risks and simply clears notifications, eroding the system's entire safety posture.
We stress that authority isn't static in this environment. When an agent is deployed, the enterprise has to treat its authority as a dynamic principal-agent contract, where that authority is always conditional and fully revocable, tied to real-time performance.
This conditionality must be formally defined in the delegation charter. This is a machine-readable, auditable policy that precisely defines the agent's action space. For instance, a procurement agent might have the authority to negotiate a contract up to a specific monetary value, but it is explicitly denied the authority to sign that contract.
Requiring a human as a service call for that final step.
Exactly.
The architectural risk here is authority drift, where agents, through, cumulative successes or accidental configuration changes, incrementally gain permissions or roles that exceed their original intended scope.
Leading to systemic overprivilege. The required mitigation is strict adherence to session-scoped tokens. These are ephemeral access tokens that expire automatically once a task is completed or after a very short time window.
So it forces the agent to revalidate everything for every new high-stakes task?
Its identity, its current delegation charter, and its authority. It prevents that cumulative creep of authority across long-running operations.
Now, let's talk about what happens when the human intervention occurs. A human override of an agent's plan is not a normal event. It's a high-signal event. It signals an alignment gap between the agent's logic and the organizational intent.
And critically, the system must be designed to prevent silent overrides. If a human manually changes an agent's output, say, editing a final document or changing a proposed value, without that change being formally flagged, recorded, and associated with the human's identity, the learning loop is completely broken.
The agent just assumes its original output was correct and remains uncalibrated.
Yep.
Therefore, overrides must be governed by an override contract.
This contract requires the human to provide a structured justification for the override using a formalized taxonomy of error types. This taxonomy might include categories like policy misinterpretation, data staleness, or ethical boundary violation. This structure is the raw, clean data used later for continuous improvement in auditing.
It lets the enterprise distinguish between an agent error and a configuration error.
Precisely. #B, the trust calibration engine.
We've established that relying on human intuition for trust in a scaled environment is, frankly, a liability. Trust has to be well calibrated.
Meaning the human's reliance must objectively and verifiably match the system's actual quantified reliability.
And that objectivity is quantified by the dynamic trust score.
This score is calculated in real time for every single agent task pair, reflecting its most recent observed performance history and its operational context. It's an indispensable measure of operational fitness.
So the trust score is not a simple average, but a weighted formula. Let's break down the key components. What's the first one?
The first is performance history. This is the verified success rate of the agent on that specific class of task over recent iterations. And crucially, success must be verified not by the agent itself, but by the governance layer.
A sustained 98% success rate on invoice processing earns a high P score.
Exactly. Second is a risk class.
And why does R act as a weighting factor on the trust score?
Because the trust required to permit autonomy for a low-stakes task like summarizing an internal memo is exponentially lower than the trust required to sign a $100,000 purchase order. Todoler weights the score such that an agent must achieve a much higher level of demonstrated reliability on high-risk tasks to maintain the same level of autonomy it enjoys on a low-risk task. It enforces risk-proportional delegation.
Okay, third is correction frequency.
$2 measures the inverse rate at which human reviewers modify or override the agent's proposed plans. The fewer the corrections, the higher the trust score. A sudden spike in human modifications indicates an immediate alignment gap.
Demanding an instant drop in the agent's trust score and its delegated autonomy.
Immediately. And fourth, outcome verification.
Which is?
Dollar measures the degree to which the agent's work is objectively verifiable by deterministic tests. Can the system run policy as code checks, unit tests, or cryptographic hashes to prove the agent achieved its goals safely?
So tasks with high verifiability are inherently less risky.
Boosting the TLR, while tasks requiring subjective judgment, like creative writing, would have a lower dollars.
The genius of this dynamic score is its direct architectural feedback loop. The trust score directly adjusts the agent's mandated level of automation.
It creates an adaptive system. If an agent consistently performs well and achieves a high trust score, say 0.8 to 1.0, the escalation engine automatically shifts the collaboration mode to level 3, human on exception, granting maximum autonomy.
But conversely, if performance drifts and the score drops,
If the $T drops to, say, 0.0 to 0.3, the system automatically forces the agent back to level 1, HITL, requiring blocking approval for every single action until its performance improves.
and this adjustment has to be mandatory even without poor performance. The system must enforce trust decay.
Absolutely. If an agent hasn't performed a specific task recently, or if the environment undergoes a major schema change, like a new regulatory update, a core API migration, a fundamental shift in input data structure, the trust score must automatically lower. This forces a revalidation period, preventing catastrophic over-reliance based on stale performance data in a fundamentally changed operational environment. #C, accountability of the provenance graph.
All of this complex scaffolding, the delegation charter, the trust score, the escalation engine, it all serves one final, overriding, and non-negotiable purpose: accountability.
Right.
The enterprise needs an immutable source of truth for every action taken.
And that source is the immutable provenance graph. This is the core of system integrity.
How is this graph structured, and what exactly does it record?
This graph links every single environmental change, whether it's a database entry, a monetary transaction, or a security configuration update back through the system. It connects the outcome to the specific agent reasoning trace that proposed it, the specific configuration parameters used, the trust score at the time of execution, and critically, the named human decision maker who intervened, approved, or overrode the action.
So in a failure scenario, particularly one involving financial or regulatory liability, this provenance graph is the legal and operational bedrock.
It has to be. It must definitively identify which actor, human or agent, provided the incorrect logic that led to the failure.
Furthermore, it governs the integrity of the feedback ingestion and learning loop. This data pipeline must include robust feedback verification to actively prevent model poisoning.
Yes.
Can you elaborate on model poisoning in this context? Is this just about bad data input?
It's worse than just bad data, it's corrupted learning. Model poisoning occurs when incorrect, biased, or even adversarial human corrections are fed back into the agent's training or memory base. For example, if a reviewer, due to lack of training or simple malice, consistently overrides the agent's correct, policy-aligned decisions with incorrect or personal preferences,
That bad data corrupts the agent's future reasoning policy over time.
making it less reliable and less compliant.
So, to protect against that systemic risk, systems have to enforce quality control on the feedback itself.
Precisely. They must require things like gold standard filtering, ensuring that only feedback provided by verified domain experts or individuals with the highest authority is used for automated tuning. Other strategies include consensus review, requiring 2 independent human reviewers to agree on a structured correction before it is written back into the agent's long-term memory or prompt templates. Accountability demands verification at every stage of the lifecycle.
Okay, so even with all this robust architectural scaffolding, hybrid teams are still susceptible to predictable organizational breakdowns. Our sources highlight several critical anti-patterns that can derail progress, often months or even years into a deployment.
Let's start with the classic failure of tuning, escalating everything. This is a safety system that's been tuned far too conservatively, maybe because of legal concerns or early skepticism, and it results in an escalation rate of over 40% of all tasks.
The impact is instant and total. System backlog, human burnout, and the immediate return of the bottleneck effect we saw in failure mode 2. The solution is rigorous threshold tuning, but also clarifying the agent's prompt constraints to reduce ambiguity and uncertainty in the first place.
And the inverse is equally insidious. Escalating nothing. This is detected when you see zero escalations on novel or statistically high-risk tasks.
And this leads to silent high-stakes failures and massive unexpected risk exposure because the triggers are either misconfigured or the agent has found a way to route around the blocking interceptor.
Right. Mitigation requires mandatory, fixed risk-based triggers that cannot be disabled, coupled with rigorous periodic adversarial testing to actively challenge the system's assumptions about risk coverage.
Then there's the more subtle failure mode that's endemic to multi-agent environments, echo chambers.
This occurs when multiple agents validate each other's decisions recursively, creating a closed loop that leads to amplification of an initial hallucination.
So if Agent A asks Agent B for confirmation on a flawed premise, and Agent B, also a probabilistic model, agrees, they've just mutually validated a catastrophic plan.
To fix that recursive validation, the architecture has to deploy independent audit agents models designed explicitly to challenge assumptions, or rely on quorum-based voting protocols where validation comes from outside the immediate reasoning group.
And finally, the purely organizational anti-pattern of liability shielding, where the human blames the agent or the agent's telemetry is ambiguous, allowing actors to deflect responsibility for costly errors.
The cure here goes back to the formal systems we've been discussing. The immutable provenance graph, signed authority tokens, and clear non-negotiable delegation charters that define who human or machine ultimately owns the outcome.
And above all, to cure inconsistency and prevent organizational infighting, the enterprise has to enforce a centralized policy registry for consistent escalation rules across all deployed agents, regardless of their domain or team.
That consistency is key. #B, the evolutionary roadmap. Achieving a truly mature, productive hybrid workforce is not a single deployment event. It's an evolutionary process. It progresses through 4 distinct phases of maturity, which the sources suggest takes 18 months or more to fully optimize and embed institutionally.
Okay, let's walk through them. Phase 1, basic escalation and approval. This is typically months 1 through 4.
The goal here is simple. Establish safety and foundational accountability. Controls are hard-coded blocking gates for all right actions and all high-risk tool calls. Metrics focus on simple measures like manual handle time and error rate. The exit criteria are met when 100% of agent actions are fully auditable and demonstrably linked to an approval or a justification.
You are optimizing for safety, not speed.
Not at all. Then you move to phase 2, risk-based autonomy. Month 4 through 10, now the system starts becoming smart. The goal is to safely scale simple, low-risk operations. The core architectural control is integrating the resource risk manifest in the impact score service into the escalation engine. The system starts dynamically distinguishing novel versus routine tasks without needing a human to pre-label them.
And your metrics track the intertwinement score and the escalation rate per objective risk level.
Yes, trying to move lower-risk tasks out of the queue.
Phase 3, trust-calibrated autonomy. Months 10 through 18. This is the inflection point where trust becomes quantifiable.
Yes. The goal shifts to personalizing autonomy based on real granular performance history. Controls include deploying the trust score engine and setting up those multi-agent critic validation loops. Exit criteria are met when autonomy levels automatically and continuously shift based on the trust score and real-time reliability metrics.
At this stage, you are maximizing throughput based on objective, verified confidence.
Exactly. And finally, phase 4, optimized hybrid workforce, month 18 and beyond. The system has achieved maturity.
This is maximum throughput with structural adaptation.
The goal is continuous self-improvement. Agents are sophisticated enough to coordinate autonomously and are capable of reframing goals when they detect a strategic conflict or policy barrier. The ultimate exit criteria are met when agents proactively identify and formally propose process improvements and rule changes to the human policy authors.
They move from being simple executors to proactive, high-functioning teammates who can influence the workflow design itself.
That's the end state. #C, new organizational roles.
This entire evolutionary roadmap requires a fundamental shift in the operating model. You have to move away from rigid functional silos toward outcome-aligned pods, dedicated teams of humans and agents focused on a single value stream.
And that requires new organizational roles with mandated segregation of duties.
The first and most crucial segregation is between the agent owner and the human reviewer.
Yes. The agent owner is the person who defines the delegation charter, sets the goals, and is accountable for the agent's output performance. They absolutely cannot be the same person who signs off on the agent's critical exceptions. It creates a check and balance system.
We also need specialized technical roles dedicated solely to the governance layer itself.
Right, the escalation designer, the engineer who models the 5 trigger types, engineers the decision packet schemas, and tunes the risk thresholds. This role must be independent of the team that develops the core AI model to maintain an objective perspective on safety.
And the person responsible for monitoring the objective measures of reliability, the trust analyst.
This role acts as the independent internal auditor for the agent fleet. Their job is exclusively monitoring the trust score, calculating calibration error, and detecting trust drift. They ensure that human reliance doesn't subtly outpace the machine's objective reliability over time, which is a constant and critical threat.
And finally, the ultimate safety role for those catastrophic fleet-wide events, the incident responder.
This individual or dedicated team handles the inevitable escalation storms and must possess non-revocable kill switch authority over all agent fleets. They must be able to revoke agent identities, halt execution, and put the system into a safe state immediately if a systemic failure or security breach is detected. This organizational structure ensures that governance capability keeps necessary pace with the speed of the technology. #outro.
We started this deep dive by examining that painful collaboration bottleneck, the gap between machine speed and human safety, and we discovered that the path to scaling safe autonomy isn't paved with magical technological fixes, but with formal, rigorous systems engineering.
We've thoroughly broken down the spectrum of interaction, moving beyond simple HITL to the highly efficient, tailored position of being on exception. We established that machine authority is never a given. It is a dynamic, revocable contract, and that human trust is not a feeling, but a quantifiable, verifiable score built on performance history, risk class, and correction frequency.
And the ultimate artifact of this entire governed system is that immutable provenance graph. By treating escalation as a formal state transition and authority as conditional, we ensure that the precious resource of human judgment is conserved and reserved only for those moments when complexity, risk, or strategic value truly justifies the cognitive cost of intervention.
The entire purpose of building this kind of robust, dynamic architecture is to move past reactive human intervention and enable predictable, productive, and safe autonomy at a vast enterprise scale.
And this leads us to our final provocative thought for you, the listener, as you look at your own complex workflows. We talked about the concept of automation opportunity mining, the powerful idea that every time a human overrides an agent's decision with the same underlying repeatable rule or logic, that human action should be seen as a policy gap. That policy gap must then be immediately converted into a deterministic business rule and automated. So this raises a crucial question for your own decision-making processes today. When you look at the decision overrides, manual interventions, or policy exceptions you currently handle, which of those are simply waiting to be captured, codified, and converted into the next generation of deterministic policy, thereby allowing your agents to operate with even greater validated autonomy tomorrow? That's where the true sustainable scalability lies.
Something to think about until the next deep dive into the systems that shape our world.
We'll see you next time.